Okay, we're going to begin this lesson. This is chapter 9 in your book, which is somehow on the subscript. There we go. This is chapter 9 in your book, and this will be chapter 9.1, labeled Using Chemical Equations. So in this chapter, we're going to be looking at the way the coefficients relate to the amount of product we have in an equation, and how much product we can get, or possibly how much product we need in order for a reaction to occur. Okay, we spent a lot of time talking about equations and reactions and making sure we can balance them. Now we're actually going to use this in a very practical sense. This is something that's used every day in real-life chemistry, where people are synthesizing compounds for commercial use. We need to know exactly how much of a certain element we need in order to get this much of a product. Okay, so that's the whole idea here. I think the best way to start this is just by thinking of something really, really simple. Say you want to make a sandwich, right? So to make a sandwich, I need 2 pieces of bread and maybe 1 slice of cheese, possibly. I like tomatoes on mine, so we'll go 1 tomato and let's say 2 slices of turkey. Now obviously you can make your sandwich however you want to make it, but this equation gives us just 1 sandwich, right? So even though our products, our reactants, these were in different ratios, we still only were able to synthesize 1 sandwich. Okay, so we can kind of write this as a ratio. So the ratio here is 2 pieces of bread, 1 slice of cheese, 1 slice of tomato, and 2 slices of turkey give us 1 sandwich. We can't build a sandwich unless we have 2 pieces of turkey, or 2 pieces of bread, or 2 slices of turkey. We can't build a sandwich unless we have that 1 slice of cheese. So it's kind of a ratio. And then in a very similar way, it works the same with compounds. So if I take any sort of chemical formula here, and for this example, I'm going to use CO, which would be carbon monoxide gas. I'm going to add it to hydrogen gas, and I'm going to synthesize something we're going to call methanol. This is CH3. OH, and this is going to be a liquid. Okay, so if I need, and I need to balance this right here. Looking at this, I have 2 here, and 4, so this would be, I need to put a 2 right there, and my carbons and oxygens are going to be okay, 1 and 1 and 1. So this is balanced now. But what it's basically saying is I need 1 molecule of CO. I need 2 molecules of H2, and my product, these 2 things together, will give me 1 molecule of CH3OH. Okay, liquid. So the whole idea here being, it doesn't necessarily have anything to do with, 1 plus 1 does not equal 2. In this case, it's 1 plus 2 equals 1. Okay, so there's this ratio we have to have in order to kind of determine what my products are going to be, what I'm going to get out of it. So if I wanted to make a very simple example with this, and say for instance, I have 3 molecules of carbon monoxide, and I have an unlimited amount of this. If I have 3 molecules of carbon monoxide, I could produce 3 molecules of CH3OH. Okay, my ratio is 1 to 2 to 1. That means for every 1 molecule of CO I produce, I can produce also 1 molecule of the product. Okay, so that's kind of the idea that we're going to look at here a little bit, and seeing what kind of things these interesting ratios can have. So I can take another very basic example and say, what if I have H2 and O2, oxygen plus hydrogen? That will give me H2O. It'll make water. Okay, Now I need to balance it, obviously. The O's are off a little bit, so I'm going to put a 2 there, and then I need to put a 2 here as well. So this says then that for every, I need 2 molecules of H2 plus 1 molecule, and I'm putting it in mole because actually it ends up working the same way, but I'm abbreviating that molecule, will give us 2 molecules of H2O. This is kind of a good deal. If I have an unlimited amount of hydrogen, I only need 1 molecule of oxygen to produce 2 molecules of H2O. This is kind of an interesting idea, okay? Which puts us in a pretty sweet spot if I'm trying to get a lot of things. The great thing about this, though, is this molecule that we're using can be counted, right? And it can be counted quantitatively, or quantitatively with an actual real number. We don't have to say it's a molecule. We might be able to say that it's simply just a mole of something. It's simply just a mole. Let's look at this. NaCl plus K2S is going to give us KCl plus NaS2. Okay, balancing this, I would find that this needs a 2, and then this also needs a 2. Okay, now before I've always said the word molecule. What if I just say the word mole? It works exactly the same way. I can say that I have 2 moles of NaCl will give me, if I have 2 moles of NaCl, it'll give me 2 moles of KCl and 1 mole of Na2S. Okay, so it's kind of this property. This is how much I need to make one of these. If you're getting confused on this, think back to the sandwich. I need 2 slices of bread to make 1 sandwich. Okay, but I only need 1 tomato to make 1 sandwich. So it's kind of this give and take, this relationship of how many you need in order to fit this kind of thing together. This is great. This is great for us. Okay, this is going to really change the way we think about chemistry a lot. Okay, so let's go ahead and do water in reverse here a little bit. So I'm going to do the equation for water in reverse. So if I break down water, I already did the one for making it, but if I break it down, I get something like this. That means for every 2 moles of water I break down, I get 2 moles H2 and 2 moles of O2. Okay? Pretty cool stuff. Now, this seems really, really simple and not very, very fun. Once you kind of start to get the whole hang of it, I screwed that up a little, didn't I? Okay, 1 mole of O2 right there. Okay, once I start to get the hang of this kind of thing where I can relate these relationships, I can actually give us quantifiable data to sort of understand exactly what I'm talking about here. Okay, and that is I can change this idea into something that's a lot more comprehensible. And that is, say for instance, I don't exactly have an even number of moles. What if I just have, the book uses this number, so I'm just going to use it. What if I have 5.8 moles of H2O, okay, and I'm going to break this down. How much H2 do I get, and how much O2 do I get? Let's go ahead and take a second to write this equation out again. We'll say 2H2O equals 2H2 plus O2. Okay, so the ratio here is 2 to 1. So for every 2 molecules of H2O I have, I get 1 molecule of O2. So this one's really, really simple. I take the mole ratio that I have, which is 5.8 mole H2O. Okay, I know that for every 2 moles of H2O, I get 1 mole of O2. Okay, which is basically going to be 5.8 divided by 2, which is, this should be a lot easier to do in my head than I'm making it, 2.6, I believe. Not 2.6, 2.9. 2.9 moles of oxygen. Okay? 2.9 moles of oxygen that would yield. How much hydrogen would it yield? Why don't you think about that for a second. If the ratio is 2 to 2, the ratio is equal, so it would equal the same amount of hydrogen. So if I have 5.8 moles of hydrogen, I also have 5.8 moles of hydrogen gas. Excuse me, if I have 5.8 moles of water, I would also get 5.8 moles of hydrogen gas. Okay, so that's the big key that we're kind of looking at here. This is the basic problem that we're going to be doing in the first part of the assignment. Then we're going to kind of transfer this over to figure out how many grams. So let's just do a couple more problems here. I'm going to do some ones that they use in the book. Here's the balanced equation. We're going to say C3H8 plus, and I'm not putting the states just because it's kind of hard for me to write that on this paper. 5O2 yields 3 CO2 plus 4 H2O. Okay? And it says here that I have 4.3 moles of C3H8, which is octane, I think. No, not octane, it's pro-tritane. I don't know what it is. Okay, C3H8 will give us how many moles of O2? Well, it requires. So how many moles of O2 do I need? Okay. Well, look at my ratio. For every 1 mole of this compound I have, propane, I was right, it's propane. If I have 1 mole of propane, I need 5 moles of oxygen in order to do the reaction. So I'm going to start with what I know. Do my railroad tracks here. Okay. I'm going to cross this out. How many do I have in the reaction? One mole of C3H8 is going to equal 5 moles of O2. Okay, so I would just take 4.5 or 4.3 times 5. That's going to equal 21.5 moles of oxygen. That's how many moles of oxygen I'm going to need for this reaction to happen. Okay, because of the 5-to-1 ratio. Okay, we're going to do one more, and then I'll cut you loose on this. Okay, if I have N2 plus 3H2, and that's going to give me ammonia. Okay, let's say for instance I have 1.3 moles of N2, and I want to know how much NH3 that's going to give me. Well, start with what I know, 1.3 moles of N2. My ratio is 1 to 2, right? So look up in my equation, how many moles do I have there? I have 1 mole of N2, and I have 2 moles of NH3. So it looks like, in this case, that 1's going to cancel out. Those labels cancel. 1.3 times 2 is going to be 2.6 moles of NH3. Okay? So that's just a basic mole-to-mole relationship used in the equations. We're going to transfer this. We're going to get a lot more detailed, but we're going to transfer this into actual something we can measure, which would be grams. So in the next video, we'll actually take these moles, convert them to grams, and see how much grams we need to make this reaction happen, or how many grams we can get from this reaction happening. Okay? But all we're looking at right now is if I have this many molecules or this many moles of an element, how much of the other element in the equation can I produce? It's highly very important to look at these, the way these things are balanced in order to interpret that. Okay?